Welcome to section 4.3, day 2, first and second derivative tests. Today's objective is to use the first and second derivative tests to identify extreme values. The first derivative test. For a continuous function f of x, we can analyze the first derivative to find extreme values. Take the first derivative and identify the critical points. Make a sign chart for f prime of x using the critical points. And analyze the sign chart to determine whether each critical point is a local max-min, absolute max-min, or neither. Here we're going to use the first derivative test to determine the local extreme values and to identify any absolute extrema. So we take our first derivative, and we get 2x minus 6. We set it equal to 0. And we get that x is 3. We make our sign chart. I'm going to put in 0 and 4 to test. Y prime at 0. And we get negative 6. We put y prime at 4. And if you evaluated this, you get 2, which is positive. By looking at our sign chart, we can tell that we have decreasing going down to 3, and then we are increasing going up to 4. So we have a critical point is 3. We will evaluate our initial function at 3. And you'll get 9 minus 18 plus 5, which is negative 4. So our point is 3, negative 4. In this, if you look at our graph, it's a parabola. It's a parabola that opens up. So this is my absolute minimum. And that is using our first derivative test. A lot of this we've already done. We're just sort of putting it all together. Next, we're going to use the first derivative test to determine the local extreme values and identify any absolutes. So we take our first derivative. Y prime is 3x squared minus 27. We set it equal to 0. And when we do that, we get 3x squared equals 27. Divide by 3, x squared is 9, and x is plus or minus 3. We make our sign chart. We have negative 3. We have 3. Put the numbers in between and below. We are then going to use our sign chart. We're going to plug in negative 4 into the derivative. So we have y prime of negative 4 is 3 times negative 4 squared minus 27. And if you do this, you get negative 4 squared, which is 16. 16 times 3 is 48. And we get a positive 21. And this is a positive. We have y prime at 0. We have 3 times 0 squared minus 27, which is negative 27. We have a negative, and then we put in y prime of 4, and we evaluate it. And when we evaluate it, we again get 48 minus 27, which is 21, which is positive. So looking at our sign chart, we can see we have increasing up to negative 3. At negative 3, we start decreasing all the way to 3, and then at 3 we start going back up. So we have a graph somewhat like this. It's a cube function. We know as we rise to negative 3, at negative 3 we have some sort of maximum, then we go down to 3, so we have a minimum there, and we're going back up afterwards. So we are going to plug in to our initial function both negative 3 and 3 and see what we get. So y of negative 3 is negative 3 cubed minus 27 times negative 3 plus 8. And when you do the math, you will find that this is 62. When you do y of 3, you plug it in. And when you evaluate this, you'll get an answer of 46. So we have the points -3, 62, and 346. This is, if you look at your graph, we're increasing from negative infinity all the way to -3. This is a local max. And then we decrease down to where 3 is, and it's at y is 46. This is our local min. And this does not have any absolutes because this is a cube function, and on the left side it's going to go all the way to negative infinity on the left side, and it's going to be going all the way to positive infinity on the right side. That's again another use of the first derivative test, finding local extremes and absolutes. Next, we're looking at the second derivative test. It says close your eyes and imagine a local max, what it looks like. And what is true about f prime of x at this point? And what is true about f double prime x at this point? Well, when you do f prime of x, you're going to find that that is going to be, when you look at f prime of x, you should see that this would be 0 at this point. And what is true about f double prime x? If we put this in here, we'd have a derivative that's less than 0 because we have a concave down at this point. When we do a local minimum, same idea. So it says here, if f prime of c, some value that we put in for x, is 0, and f double prime c is less than 0, f has a local max at c. So if we do both things, f prime of c is 0 and f double prime of c is less than 0, we have a local maximum. And then f prime of c is 0 and f double prime of c is greater than 0, f has a local minimum. So we're going to use these to answer questions using the second derivative test. So it says use the second derivative test to find the local extreme values of this function. So first we're going to take the first derivative, and y prime is 3x squared minus 12. We are going to set this equal to 0. And you should find that your critical points will be at x equals -2 and 2. These are my critical points. We will put the -2 and 2 back into our original function and see where our points are. So y of -2 is -2 cubed minus 12 times -2 minus 5. And when you do this, you get 11. And we put in y of 2 and evaluate. And when you do this, you get -21. We're going to take the second derivative, and y double prime is 6x. And what we're going to do is we're going to take these critical points, -2 and 2, and we're going to plug them into our second derivative and see what we get for our signs. So y double prime of -2 is -12, which is negative. We have y double prime of 2, which is 6 times 2, which is 12, which is positive. So we have a negative sign and a positive sign. Because we have a negative sign here, it means this is concave down. And it also means because it's concave down across this area, this is a local max. And if you think about this, our graph would look like this in this area because it's concave down. At 2, we have concave up because our sign is positive, and this means there's a local min. And for this part of the graph, it would look like this. Because we're concave up, that means we have a local min. When we do the second derivative test, we find our critical points from the first derivative, and then we plug them into the second derivative. If you're ever asked to use the second derivative test to find extreme values, you will find the first derivative, find your critical points, then take the second derivative, plug the critical points into the second derivative, see what your signs are, and that will tell you if you're concave up or down, which will also tell you if you have a max or a min. Here it says use the second derivative test to find the local extreme values of the function. So we take our derivative, we get y prime is 15x to the fourth minus 15x squared. We're going to do some factoring. We're going to pull the 15x squared, leaves x squared minus 1. And you set this equal to 0, you'll find that your critical points are at x equals 0, -1, and 1. So we have 3 critical points. We would plug them back into the original function, and we'd have f of 0. When you plug it back in, 0 minus 0 plus 3 is just 3. We will plug in -1. When you plug in -1, you get the first side would be -3 plus 5 plus 3, and you get 5. And then you have f of 1, and you get 3 minus 5 plus 3, which is 1. So we have our points are 0, 3, 1, 1, and -1, 5. We will do our second derivative, and we have y double prime is 60x cubed minus 30x. We will then plug in our critical points. We'll do y double prime of -1 first. And we do this, you get -1 cubed is -1. We have -60. And then we have plus 30, but this is a negative number. Then we have y double prime of 0. And if you plug 0 in here, you get 0 minus 0, which is 0, which is inconclusive. We do not have a sign here. And then we have y double prime of 1. And if you plug that in, you get 60 minus 30, which is positive. Since we have this inconclusive piece, we are going to use a sign chart to see what's happening. So we have our critical points at -1, 0, and 1. And we would plug in, let's say -2, -1/2, 1/2, and 2. When we use this sign chart, we're going to use the first derivative. So we're going to plug in -2 to the first derivative, and if you do that, you will get a positive here. If you plug in -1/2 into the first derivative, you'll get a negative. If you plug in 1/2 into the first derivative, you'll get a negative. And if you plug in 2 to the first derivative, you will get a positive. So what this is showing us is that we increase until we get to -1, but then we're decreasing all the way until we get to +1, and then we start going back up. Because we don't have a sign change at 0, we have a negative on both sides of it, we are steadily decreasing between -1 and 1. So this is not going to be an extreme value. This is called what we call a stationary point, because there is no extreme here and we have the same side on both sides, and this does happen. So using our first derivative into our second derivative, we have a negative here. This means this is concave down. And we have a local max. At -1, at -1.5. We have a positive for our second derivative at 1. So this is going to be concave up at 1. And we have a local min. And our local min is 1, 1. And if you look at my sketch of my graph, you'll see we're rising as we come in from -infinity to -1. And then we're going down all the way to 1, and we're going back up. That's why there is no absolutes in this graph. And we only have locals. All right, that is the second derivative test, and we found here that sometimes when we do these sign charts with local derivative, we do not have a change in sign, and we call those stationary points because there is not a local max or min at that point. So here's your assignment. So identify extreme values using the first and second derivative tests. Thank you for watching, and have a nice day.